This is the setup for verification of Maxwell's reciprocal theorem for a cantilever beam. Already I have given sufficient explanation how to take down the readings from the dial gauge, how to verify this Maxwell's reciprocal theorem for a simply supported beam. Okay, only support changes the way you note down the readings from the dial gauge and the way you add the weight, the way you plot the graph, everything remains the same. Okay, everything remains the same. Okay, so here the figure shows the left end is fixed, okay, and the other end is free. So we call it as a cantilever beam. So you can take random points anywhere, 2 points along the length of the beam, cantilever beam. Okay, let us make this as point 1 where the weight anchor is placed, and let this be point 2 where the dial gauge is fixed. You keep on at the weight. Procedure already I have told and explained for this simply supported beam. Same procedure, just to add 0.5 kg, note down the reading, and again you add one more 0.5 kg, and for total 1 kg you note down the reading. So like this you just keep on add the weights in the range of 0.5 kg. You can take 5 readings, okay, and interchange this, bring this dial gauge to the left hand, point 1, and take this weight anchor to the right hand side, point 2. Now you add the weights in point 2, weight anchor step by step, 0.5 kg, 0.5 kg, note down the readings. So, so that you can measure the deflection at point 1 due to load at 2, and deflection at 2 due to load at 1. So like this, you can verify the Maxwell's reciprocal theorem. And I have taken one a close photograph of this dial gauge. You can see here the bigger pointer points the 0 here, and the smaller pointer points the 0. So when this, as I told you earlier for simply supported beam, when this bigger pointer gives one complete rotation, means that is 100. Okay, 100 into 0.01 is nothing but 1 millimeter. Okay, 1 millimeter. So when this goes one complete revolution or rotation, this smaller needle would have been moved to 1, which means directly you can take it as a 1 millimeter. So before adding the weights, once you fix the beam, the dial gauge, and the weight anchor, you should ensure that these two needles are in 0 position. Very important. And these are the same procedures which I've given for simply supported beam. Same procedure, exactly same. Okay, so here the figure shows that you add a weight at 1, measure the deflection at 2, and figure 2 shows that add a weight at 2 and measure the deflection at 1, which means that deflection at 1 due to load at 2 must be equal to deflection at 2 due to load at 1. Okay, so which is nothing but delta 1 2 is equal to delta 2 1. We are going to verify it experimentally. Okay, and by strength of metal approach also we are going to verify it with the help of MAXWELL'S method. And this is the procedure which I have explained you already in simply supported beam. Okay, and the same procedure you're going to follow it, and these are the readings. Okay, so you can see here the weights are added in the range of 0.5 kg during loading. These are the dial gauge readings, and during unloading these are the readings. Take the average of this and convert this to millimeter by multiplying by 0.01. Okay, 0.01. Similarly, interchange the weight anchor position and dial gauge position, and add the weight anchor, note down the readings, loading, unloading, take the average, and convert that to millimeter. Now plot these two, delta 1 2 and delta 2 1, in a graph. Okay, in a graph, that is load versus average deflection in millimeter. Okay, so you could get these two blue color and brown color plots, and just go to the Excel sheet. I plotted this in Excel sheet. You generate a straight line, okay, and generate the equation, straight line equation. You can see here y is equal to mx plus c, and here also the straight line equation. You can check with the help of the slopes 0.514 and 0.516. So our slopes for both these delta 1 2 and delta 2 1 are equal, we can say. If you consider first two digits, we can say it is equal. Okay, so hence the Maxwell reciprocal theorem is verified, we can tell. And this is by Maxwell's method. We can verify by Maxwell's method for this cantilever beam. So cantilever beam subject to load 100 Newton in the free and distance of 0.4 meter. So again here the second case, 100 Newton is applied at a distance of 2 meters from the free end. and you've taken a section xx and a distance x to the Pn, and bending moment equation is returned, then integrate to get slope equation, then again integrate to get the deflection equation. The final deflection equation is this, and we arrive at deflection at point 1 to be minus 108.33 by EI. And again, just shift this load to point 1 and we measure the deflection at 2 due to load at 1. Write down the moment equation, integrate it again twice. Then find the constant of integration C1 and C2 by applying the boundary conditions. Then we arrive this final deflection equation. Then at point 2, x is equal to 0.5 meter. We arrive at deflection y2 is equal to minus 108.33 by EI. Hence, the Maxwell's reciprocal theorem is proved.